Good morning, everyone. Thank you for being here today. My name is Hongbin Lin, and it's my honor to present my PhD thesis, Mastering Visuomotor Grasping with Word Models for Surgical Robots. I would like to begin by expressing my gratitude to the committee members, Professor Liu, Professor Ao, and Professor Dou, and Professor Yu. So thank you all for your time and guidance. With that, let's begin. So in recent years, surgical autonomy has great advance in the diverse surgical tasks. It has works from the CUHK, the visual parsing perception regressor, policy learning, and Visuomotor controller, and the work from the Johns Hopkins, the hierarchical surgical robot transformer. So these work automate subtasks in the surgical procedure, relieving the burden of the surgeon and improving the consistency of the surgical outcome. So in this thesis, we investigate fundamental and frequent action in the surgical procedure, grasping. It occurs when the surgical tool required to handle the needle, gauze, thread, and the tissue in the surgical task. So in the robot-assisted surgery, the grasping action can be autonomous for suturing, repair, debridement, tissue dissection, and retraction. So researcher has extensively explored the surgical grasping automation using the pose-based method and the visual feature-based method. So these approach track low-dimensional spatial states such as the object pose or the handcraft image space features from the visual input and fed them to the downstream controller. So however, they face the limitation. First, they often rely on the geometric model and assume shapes, which limits the generalization to unseen object and introduce the bias. Second, the state estimation is sensitive to the visual disturbance, including the occlusion, fogging, and blur. Third, for the low dimensional state, they struggle to represent the deformation object configuration. So some approach rely on the robot proprioceptive measurements such as the joint measurement to infer the grip pose. So these methods suffer from the inaccurate robot measurements due to the potential-based sensing, hysteresis, and mechanical slack, which degrades the control performance. So Visuomotor learning offer a promising alternative to pose-based and visual feature-based methods, showing a strong performance in the general robot grasping. These methods learn end-to-end policy that maps the visual observation directly to the robot action. Implicitly capture the spatial feature that often have a richer than representation than the implicit representation such as the pose and the handcraft features. As the result, the Visuomotor approach demonstrates improved generalization to the out-of-distribution object, enhance the robustness to the visual noise, and the ability to handle the deformable objects. Despite the success of the visual motor learning in the general robotic grasping, applying it to the robot-assisted surgery face domain-specific challenge. First, in the typical robot-assisted camera setting, the task-related pixel on the observed image are relatively scarce. With the ratio of the task object, it will be less than 1%. In such a low signal-to-noise ratio pose a significant challenge for the training. Second, the surgical grasping require millimeter level for the precision and the safe trajectory to prevent tissue damage. Third, the surgical environment are significantly more complex with the patient-specific anatomy, dynamic scenes change, and the frequent visual occlusion, as well as the unpredictable tissue dynamics. So these will change both the perception and the control. Lastly, data collection in the surgical robot have a high cost in the human labor and operation. So there are a few works in the field of the Visuomotor learning in the robot-assisted surgery. The first work is the transformer-based policy trained via the imitation learning and applied to the surgical scene in both the phantom and ex vivo setting. But it requires extensive real robot data collection, incurring the high labor and operation costs. Moreover, it relies on the additional wrist mount camera, increasing the hardware the complexity beyond the standard RAS setups, which concern the feasibility in the in vivo setting due to the port constraint. Another work is to train a visual motor learning policy in the simulation using the PPO and then transfer it to the phantom scenes via the pixel level domain randomization. However, its applicability to the ex vivo setting remain unclear, and especially when it relies on the real sense camera, which might be not suitable for the surgical environment. So in this thesis, we aim to address 4 challenges beyond the prior works. The first is the sim to real transfer to an ex vivo setting. This can have no reliance on the need of the real robot data collection. The second is only from a single stereo camera pair, which is accessible for the standard RAS setting. Third is the object agnostic grasping without the need of the object-specific information. And the fourth is the semblance efficiency for the visual motor learning, which reduce the training data and time. So our goal is to control a robot arm with arbitrary gripper to grasp an arbitrary target object within the workspace. The observation is the stereo image and control the gripper with the robot action. The success we consider success if the object is grasped. The gripper and the target object can be randomized within the workspace. We only use the single camera with the stereo camera pair, and we use the delta action. We assume the jaw limit will not exceed the robot during the procedure, and the target object and the gripper can be partially occluded but not fully occluded. The pose of the gripper or the target object cannot be tracked explicitly. So we formulate the grasping problem with the palm. The observation include the high dimensional image from the stereo camera and the low dimensional observation like the jaw state, controller state, and final task state. In our case, the jaw measurement pose is not observable. The action space includes a discrete delta action with 9 elements. So we use a sparse reward in our POM. The termination and the sparse reward is determined by 4 task level states. We lay out the overview of 3 works in the thesis. For perception, we process the RGB stereo image with the visual perception pipeline. For training and control, we use a hybrid control architecture for robot actuation. Furthermore, we use domain randomization applied in simulation training. For symmetry, we augment the demonstration trajectory with our symmetric prior data augmentation for the training. Now we introduce the first word, perception of the visual motor policy for general surgical grasping. We investigate the word model architecture for visual motor learning. The word model generates the simulate experience, including the temporal image observation, and use the simulate experience to train the visual motor policy. In most of the word model architecture, they use a compact image with the size of the 64 by 64. The first reason is that it is challenged to learn a long horizon video prediction. In addition, they typically use a VAE for encoding, which is notoriously hard to scale to the high resolution image. Finally, the compact image improves the sample efficiency and the computation complexity. A common implementation is to downsample the high-quality RGB image to the compact RGB image and feed it to the word models. However, downsampling image leads to significant image quality loss. Furthermore, it changes the encode spatial information from the RGB representation. So we propose a pipeline
you
for.
may need to speed up a little bit more.
Okay. We first estimate the depth and segment mask from the RGB image, and after that we project the depth and mask with orthogonal reprojection. Finally, we use the novel image representation for visual motor policy. For that estimation, we use a SOTA method called the IGVE, which infer the depth image from the stereo image with the pre-trained model. For mask segmentation, we use a SOTA semi-supervised video of object segmentation method called track anything. The method includes two stages. We annotate the mask, and then with the mask can be created via a few point prompts. The second stage is the online tracking. Given the annotation, the model can track the object mask automatically. So it is robust to the occlusion and out-of-frame cases. So after the depth and mass estimation, we project the image onto the equilibrium point. So equilibrium refers to the property that apply the group action on the input space of the mapping have the same result of the applying to the out space. So in the case of the convolution network, transforming an object in the XY axis and then encoding in the image into we will use the same feature maps as the encoding the original image and then translating the feature map. But CNN do not equivalent in the translation of the Z-axis. So in the perspective projection, the image is formed by the radiant beams converging to the focus point. The projection suffer from the shape scaling. When the object is near, the shape is large, and it is far when it is small. We project the image with the voxel-based orthogonal projection using the Z-axis equivalence for the CNN. First, we infer the point cloud from the depth image based on the camera parameters. Then we voxelize the point cloud. Finally, we orthogonal project the voxel to get the depth image where the projected beams are parallel. After that, we use the projected image. We need to find the compact image representation for the Visuomotor input of the Visuomotor policy. We need to maintain the high resolution in the critical local region, such as the vicinity of the gripper, while satisfying the compact image set size constraint. We propose an image representation for called the dynamic spot adaptation. We zoom in the projected depth and mass with a square mask. The zoom-in mask centroid align with the center of the gripper pixel. So we also broadcast the low-dimensional observation signal to the image plane. After that, we downsample the image to the compact image resolution. Now we introduce my second work, training and control. Leverage the modern word model architecture, DreamerV2 for the Visuomotor learning. In this framework, observation is encoded into the discrete latent space with VAE, and the latent state is predicted by the recurrent state space model. So it shows a SOTA performance over the model-free methods like PPO in the general manipulation. We propose a hybrid control architecture to deal with the issue of the slow conversion caused by POM, suboptimal policy due to the policy stochasticity and the poor performance at the beginning steps. We integrate our learn policy with the traditional control methods. So in the DreamerV2, the initial estimation latent states are set to 0, and which cause a large error from that of the ground truth. So the poor estimation in the latent space leads to the poor performance at the beginning of the steps. So in our control, we classify it as the beginning step, and we use a idle policy to keep the robot same configuration. This ensures the robot will not damage the environment when the estimation state is poor. So after the beginning step, we will define as either the PID phase or the learn policy phase. We use the difference of the voxel-centroid coordinate between the gripper and the target objects as the distance matrix. So that when distance is beyond the predefined threshold, we define it as the PID policy. The PID policy actuates the robot gripper to approach the target object. When the distance is within the predefined threshold, and then we use our learn controller to actuate the robot. There is a safety concern in the grasping. That is, the gripper might hit the platform beneath the target grasping object, which leads to the potential damage. We apply a simple safe control for this issue. We track the difference of the Z voxels centroid coordinate between the gripper and the target. So when the difference is smaller than a certain safety threshold, the gripper will move up by 30 millimeters. Now we introduce the simulation training scene. We build our simulation on the SOTA platform called Soro. We share the same features like needle picking, the physics engine, manipulator, and instrument. We also develop new features, including the randomizing the initial heights of the target grasping object, limiting the maximum trial, and remove the sensitive measurement and the new target object like the block and rod. In addition, we use a 45-degree tilt orientation for the gripper to enhance the gripper visibility relative to the stereo camera. We deploy 4 types of the domain randomization. The first is the camera is randomized to simulate the error in the calibrate camera extrinsic parameters. Second, we scale the object size to adapt the size variance of the target object. Third, we add an action noise to the gripper to simulate the error between the measure and design robot actuate position. Lastly, we add the image noise to simulate the estimation error in the depth and the segmentation. For the training recipe, we've prefilled the replay buffer with the demonstration and random policy. We train 1.1 million steps, and the rest is the same as the Dreamer V2. For the baseline, we evaluate the SOTA baseline, including our previous work guess, the model-based RL Dreamer V2, and model-free baseline PPO. We also evaluate the ablation baseline for our individual components. So during the training, all the SOTA baseline do not improve to the positive return. So in contrast, our method improves steadily to a positive return of the 0.25. Now we introduce our third work, leveraging the symmetry for visuomotor learning in the surgical grasping. So in the palm, there is a symmetric prior where the transforming the condition of the palm with the isometric group remain invariant. This symmetric prior can be used for data augmentation and designing the equivariant model, improving the sampling efficiency of the visuomotor policy. However, isometric group transformation remain fixed between the task object and across time steps within a trajectory. This limits the variance in both the spatial and time dimension. Field study explored the non-isometric group symmetry, which apply the non-fixed transformation in the spatial and temporal dimension. So previous work studied the picking as the one-step decision-making and pick and place for the two-step decision-making. However, it remained unclear for the multiple steps, more than 2. We propose a new formulation for the non-isometric group transformation in the setting of the multiple steps. The symmetric prior is formulated as the transforming the condition of the palm with a 9-ohms isometric group remain invariant. All group elements in the transformation are mutually independent. We propose a novel data augmentation leveraging the non-isometric symmetric prior. Our augmentation satisfies the validity of the palm using the multi-phase augmentation during the imperfect phase symmetry of the task. In addition, we augment the state in a reverse time sequence to deal with the consistency of the sparse delay reward. We also used a structure action for data augmentation. The translation action is transformed by the radius and height scaling, as well as the Z rotation. The rotation action is transformed by adding small noise. So our structure action can improve the diversity of the data augmentation, such as uniformly sampling the entire state space. It also improves the relevance of the data augmentation, such as reducing the jerky motion in 2 consecutive time steps. Compared with the isometric method, our augmentation yield a larger sampling space. This relaxes the limitation of the isometric augmentation and improves the overall learning performance. Finally, we integrate our non-isometric augmentation with the isometric method. We create a new group space that contains both the ISO and non-ISO group space. Then the palm is the multi-group invariant with respect to the new group. We integrate the isometric model in the network architecture. We also integrate the augmentation like the random rotation. We evaluate our method on the palm manipulation task, including the block pulling, picking, and drawer opening. There is one movable and immovable object. The movability is unobservable. Our method improved the performance by over 25% compared with the isometric method. Meanwhile, it reduced the demonstration by the 97% without the performance degradation. We also evaluate our method in our surgical grasping task. We show a 50% improvement in the performance compared without the method of the augmentation. In addition, we show significant reduction in the demonstration data by 99% and the training time by the 55%. Now we introduce the application in the laparoscopic robot-assisted surgery. So in simulation, we train our scene with our different random seat. We conduct a performance study using in distribution target object. Our method achieves a strong performance with a success rate above the 50%. We also conduct a generality study in the simulation to evaluate our distribution size, shapes, and the target object. Our controller experienced only a slight degradation with the maximum of the 4% success rate. This highlights a strong generality. Lastly, we conduct a robustness study. We evaluate the setting of the moving camera during the grasping and a regrasping setting with one or more than with a two grasp trial. So these two disturbance only experience 5% of the success rate degradation. So this performance, the performance gain highlight the robustness of our controller. So we evaluate the sim to real transfer for our controller. For real robot, we deploy our controller to the DVRK. The grasping task is carried out on the two types of the phantom base platform, a square phantom and a multi-level phantom, as well as on an ex vivo animal platform using a porcine stomach. The square phantom is a silicone platform measuring the 10 centimeter in both width and height. In the performance study, we evaluate in the in distribution object. Our controller achieved a success rate of 75%, outperforming the soda baselines, which achieved only the 0 success rate. In addition, the ablation baseline showed the great success rate compared to our controller. To evaluate the generality, we evaluate our controller to adapt our distribution target object, OOD gripper and OOD camera pose. For the OOD target object, we test 5 types of the target object as needle, thread, gauze, sponge, and debris. We achieve a success rate of above 65%. Among all the target object, grasping thread is the most challenging. For all the camera pose, we evaluate the two unseen camera pose, where the z-axis of the camera is tilted by the 0 degree and a 40 degree. There is no degradation in the 0 degree and a slight decline of the 5% in the 40 degree. For the OOD gripper, we evaluate our controller using an unseen instrument gripper, a forceps gripper, performing a slightly decline of the 5% compared to a performance study. In the robustness study, we conduct a study in the visual disturbance. The square phantom is wrapped by 2 print papers to simulate the RAS background. We also apply the camera pose noise, the image noise for the disturbance. The visual disturbance only experience a minor degradation of the 10% of success rate. We conduct study in the control disturbance for target noise disturbance. The square phantom is positioned on the motorized rotating platform. We also apply the action noise for the study. These two types of disturbance experience a maximum degradation of the 15% of the success rate. This highlights the strong robustness of our controller to the control disturbance. In this study, we investigate whether the controller can grasp an object placed on the platform with varying height. So we design a platform with a height difference of 4 centimeters. The width and height is also 10 centimeters. we conduct a performance study using the needle. Compared to the square phantom, all target object experience only the 10% of the decrease in the success rate. So grasping needle remains the most challenging. The minor degradation highlights how the controller can adapt to the platform height. We designed this experience to evaluate the controller effectiveness in the ex vivo setting. We use a porcine stomach measuring the 20 centimeter by 20 centimeter. In the performance study, we used a needle for grasping. We show a 65% of success rate. So compared to the square phantom, our ex vivo study only experienced a moderate decrease of the 5% in success rate. This highlights a strong performance in the ex vivo performance. For generality evaluation, we evaluate the controller on the various target objects, including the thread, goal, sponge, and tissue. Our controller achieved a success rate of the 77.5% success rate. Among these objects, grasping tissue is the hardest, with the 55% of success rate. This might caused by the visual pattern of the tissue is similar to the background. For the robustness study, we evaluate three types of the disturbance: the background, inserted needle, and the blood occlusion. For the background disturbance, we vary the background height by adjusting the platform orientation and deforming the movable organs. As the result, the background can be changed. For the disturbance of the inserted needle, the needle is partially inserted to the tissue of the porcine stomach. For the blood occlusion scenario, we partially submerge the needle in the blood of the surface of the porcine stomach. Our controller achieved 58.3% of the success rate for the robustness study. So among this study, controller show no performance degradation under the background disturbance. For the rest two disturbance, we experience a moderate degradation of the 10% drop. So we qualitatively evaluate our controller in a human phantom, which showcase the potential application in the in vivo setting. In summary, we introduced three works, including the perception, training, and control, and leveraging the symmetry. We applied this work in the setting of the laparoscopic robot assisted surgery. So here we show our publication. So our
Can you
yes.
say a little bit longer for your publication so that
Okay.
people can see? Yeah. You just need to tell people what you have done.
Yeah, for the we are submitting to the IGRR for the first two work and the TRO for the third work. And this is the previous publication here. And I also participate the CUHK science robotic paper. Yeah.
Okay.
So our contribution has fivefold. We propose a perception pipeline for the visual motor learning for surgical grasping in our data-driven framework. And we also propose a hybrid control architecture for visual motor learning of the surgical grasping in the framework. For the third contribution is the novel formulation for the non-isometric symmetry within the POM framework, and we also propose a data augmentation within the framework. The evaluation of the symmetric method, we conduct experience on the two domains, including the general manipulation and the surgical grasping. So we are the first to showcase the leveraging the non-isometric matrix in the multi-step decision-making problem in the field of the general robot manipulation. And we are also the first to showcase the effectiveness of the leveraging symmetric pry in the field of surgical autonomy. We also evaluate our data-driven framework here, and we showcase the performance and generation and robustness. We are the first success deployment of the Visuomotor policy transfer to the from the simulation to the ex vivo setting, using only the visual input from a standard pair of the endoscopic camera. Yeah, and for the future work, we will try to integrate with the latest work like the latest techniques like the VLA to improve our control frequency. So our control frequency is only 1 hertz, and we can improve the control frequency using VLA. Second, since we still need to label the mask, so we try to explore the unsupervised video object segmentation in the future. And here we try to explore the multi-group equilibrium model. So now we only implement the data augmentation. We will extend to the equilibrium model for the future. And use for our three works, we will try to extend to the in vivo animal study beyond the ex vivo. And then we will try to use our framework, data-driven framework, to explore to extend to other surgical tasks such as the needle insertion and thread looping. So thank you for listening. Here is the Q&A section.
Okay, thank you, Mr. Lin. Now we move to the Q&A session. As usual, we would like to ask an external examiner to ask a question first. Michael,
Okay.
yeah.
Yeah. So I actually forgot the exact context. This is an open session for everybody, or is there a closed and open session?
It's for everybody. Yeah. You
So
can.
we have session.
Yeah.
We have two sessions. One is open, and then we also have a closed session later on.
Yeah. If you want to do some closed session, that's fine. Yeah.
You can save some. So what we normally do, Michael, is the first like maybe 20 minutes, we will let people to ask questions from open session perspective. And then after it is done, we will have a closed session. We can also further to ask Hongbin or Ben more in-depth question only for the committee member.
Okay. Yeah, I guess I'll just ask one question for now, which is I believe most of what you showed was with like one instrument. Have you looked at how to scale to multiple arm, multiple instruments?
Yeah. Actually, I have generated study for the instrument gripper like the forceps gripper. I think we have showed the demonstration.
Oh, I mean
Here.
like bimanual.
Bimanual. No, we haven't extend to the bimanual yet, but we have like evaluate the on the out of distribution instrument gripper like the forceps.
Mhm.
And
Yeah.
it showcased like the generality.
Right. Do you think that with a bimanual setup or with even a third arm, does this apply directly, or do you think that you would need retraining?
I think definitely we need to retraining, and I think the bottleneck should be the perception pipeline. So right now we have considered only the one gripper. So we have a zooming mask there. Let me change to that script. Here. So we propose a zooming mask. So the mask will follow the gripper coordinate. So when the gripper move, the mask will move accordingly. So right now we only support for the single arm. And I think in the future we need more layers for supporting the multiple arms to track more arms. It can be done easily, but you cannot directly do it without changing the algorithm.
Right. Okay, thanks.
So for other committee member you have or from the floor? I say not several students or others are joining. So, any question from the audience? Oh,
May I ask a question?
sure.
Go ahead.
Yes.
Ben, were you surprised by the results of and the reduction of demonstrations needed for you to compute sort of performance? Because obviously the 99% reduction in demonstrations is significant.
Mhm.
How does that come across to you?
I think definitely here we showcase the reduction of the demonstration without the performance degradation. So yeah, definitely our method have a huge impact on like this field. But yeah, but I think we will can do more like integrating the equivariant model. So we only like implement the data augmentation, which is only it will not enough to take full advantage of the multi-group theory. So I have a bunch of theory behind, but it remain unused. So I think it would be used for the future work.
Thank you.
Yeah.
I may have a general question. Maybe it's good for other people to ask similar question. So when I look at the video, you normally have overshoot.
Overshoot.
You grasp something, you overshoot, push against the tissue.
Yes.
But human surgeon doesn't have overshoot in general because you don't know what kind of tissue you are touching. And then I know you are trying to, I think that's maybe a general practice in AI person. They just focus on the successful way on the grasping something or
Yes.
pick up task. But
Yes.
but if we add additional requirement like don't touch on any tissue at all, can we add the boundary there? Like in optimization, we can kind of add some constraint, hard constraint, so that we don't touch any tissue. Do you think if I don't know how you can add constraint here. And that's the first question, how you can add constraint. The second question, is if we add more constraint, do you think the successful way will drop significantly?
Yes, that's a good question. And I think the first bottleneck for me is the depth estimation we are using is not accurate enough. Like our human eye, we can accurately know the depth of something, or we can feel the depth of something. But in practice, when we using our depth module, the controller need to first like hit something, or they find the some of the state of the target object is changing, and then it feel like okay, we are grasping something.
Maybe I rephrase the question.
Okay.
It's not just the depth, it's the objective. Well, now you only have one
Okay.
objective, which is grasping
Okay.
the object. But if we also pay attention to the to touching on tissue when you are grasping something, that means you have multi-objective starting from now.
Yes.
So
Yes. I think that's the right now our goal is only the success rate. We care about the success rate. Uh, when if we include more matrix like the tissue deformation, we can grasp the object without applying too much pressure on the tissue. But I think it will be our future work to integrate multiple objectives.
no
But
problem.
yeah,
That's good. Thanks.
but
Yeah.
right now we don't have the matrix to like describe the tension of the tissue. Yeah.
Yeah, actually, I want to ask this question, because your success rate is high, because the supporting your tissue, you
Mhm.
use the deformation so that you can really raise up the success rate in grasping. So if the needle put on the hard surface, So what's the success rate? This actually is much more challenge compared to your grasp needle on the tissue surface.
Yes, yeah. That is your expert, and I think grasping something on the soft platform is much easier than grasping something on the hard platform. In terms of that, I think, but in the surgical autonomy, most of the cases we're dealing with the deformable objects.
Yeah, I understand. But as Professor O mentioned about,
Yeah.
if really interact tissue, during the grasping, there could be some concern. You could damage the tissue. You might it's not desirable to really contact the tissue during the grasping. Ideally, yeah.
Yeah, I think there is one point I think I can emphasize is we have some concern about the safety, and we have some design for that. But I think it's really naive that for our design. For this one, I think we consider the the platform. We consider the distance between the gripper and the target object, and the target object has some distance between the target object to the platform, so we can roughly estimate the distance between the gripper and the platform. I think when the gripper is too close to the ground, and it will be moved upward by the 30% of the 30 millimeter to try to prevent it from putting too much forces on the tissue. Yeah,
Okay.
I think that works for me, but I think in the future we will have more works for this kind of the safety control.
Thank you. Sounds like you have some way to solve that problem. You should say it at the beginning.
Okay.
Yeah, but it's too naive, and I think
I know, I
people.
mean, it's a good start. It's a good start. We just need to know if you have some idea about how to handle it properly. Yeah.
Yeah.
Yeah, I have a general question. You mentioned about you work in three aspects, right? So
Yes.
can you summarize the which one is most important contribution in the thesis? It seems to me the first part, perception part, you just use the conventional approach, right?
Yes.
Implement in this case, and then in the second part, I fail to catch up the contribution. It seems to me also you apply existing approach in this particular task, right?
Yes.
Some contribution in the third part. So which one is more important?
Yeah.
The most important one, contribution for your thesis work.
Yeah, from my perspective, I think the first one, the perception one, I have more contribution in terms of the novelty for the surgical autonomy. We propose a pipeline, and a few of the component is novel, and this is from the perspective of the surgical autonomy. But in terms of the leveraging the symmetry of the visuomotor learning, we have a bigger compact in terms of the theory of the contributing the theory of the visuomotor learning for the general robot manipulation. So that beyond the surgical task, we can extend it to the more general robot manipulation field. Is that answering your question?
Okay, you mean the first part? Your
Yeah,
most important
for our theme, we are doing the surgical autonomy. So yeah, the first part we are have some.
part. But it seems to me that you are using existing model. Maybe we can just more.
Yeah, but yeah, you're right. You're right. I think we have some. We don't claim that using our existing work is our contribution. Instead, we like the image reprojection is novel to me, and then the image representation using the dynamic spotlight adaptation is novel. So these two work is something I propose, and we evaluate in the surgical task.
Okay.
Yes.
Yeah. So this dynamic spotlight adaptation. Can you explain a little bit more?
Yeah.
Because the most important contribution I'd like to know more.
Thank you for your question. And this representation solving the issue that when we try to use a compact image like the 64 by 64 by 3, we directly downsample it. It will be too blur, and the needle, since the needle is really thin, and the needle will lose a lot of the information. So instead, before we downsampling, we first try to zoom in the vicinity of the task-related objects. So, but the object is moving, right? And you need to find a way to track the object.
Okay.
And
So
zoom in.
in summary, is that you try to detect the ROI.
That would be ROI for the
use
computer
ROI
vision.
to try to without just the direct downsampling, and then feed in the small region to the network, right?
That would be ROI
That's
for the
right.
computer vision. And I think we just use a simple way to locate the ROI.
Yes, you have some approach to locate the ROI and
Yes.
feed it into the existing network. So is this the most important contribution for you, from you, or
the most important? And I think
your contribution in your work. I just want to make sure.
And this image reprojection thing, and we project the image on using the orthogonal projection, and the image will be equivariance in terms of the z-axis. So it will have no shape scaling effect.
Okay, but works-based orthogonal projection, the approach is already there, right?
But we are using the voxel base, and we showcase the this is equivalence form. I think there is a lot of other way to do that. And we propose a voxel-based method, and we showcase that this is a equivariance in terms of the z-axis, and CNN can be much easier to learn a image with a z-axis equivariance form. It will require less data, and it will have a better performance.
Okay, you compare this approach with the sort method. Did you compare?
Compare with the SOTA.
Compare your approach with the SOTA approach.
Right now, not yet, but it will be in our future work. We showcase the effectiveness using the ablation baseline. So without this one, it will be worse, much worse, and we try to demonstrate the effectiveness.
Okay. Okay. Any other general question? Any question from the audience? Oh, Duqi, you have any question during the open session, or you want to?
I keep question to the closed door.
Okay. So if not, so may I ask the audience to leave? Only a committee member stay, please.
Do I need to leave now?
No.
No, you don't need to. We are going to grill you.
Okay.
Okay. You have plenty of time.
Okay.
Yeah. Well, who is Chen Yanning? Can someone kick the host? Chen Yanning.
Hello. I don't have any questions.
No. Please.
So you need to quit.
You need to leave.
Okay. Thank you.
Yeah. Okay. Now we start close session. Michael, from Michael Ye, you have some question to ask?
Yeah. So I think on slide 10, you were saying that you were using discrete actions. We've sped by really quickly. So it was discrete actions on On what?
Is that the slide?
Yeah, here. Yeah.
Yeah, this one.
Yeah.
Okay.
So this action space, you have so you have high dimensional observation and then you have discrete. Why the discrete action space?
Yeah, there will be there is some work saying that using the discrete action can improve the sampling efficiency of the visuomotor learning compared to continuous action. And
Yeah, but we're also talking about very precise, object manipulation here, right? So that's the thing that was a little confusing to me because whenever I'm thinking about like robotic surgery, the idea of discretizing and getting a lower resolution is something that seems it's a choice that like would come with a lot of downstream, reduction in precision. So that's why I'm just wondering on this side.
yeah, you are right. I think there will be great potential using the continuous action. I think because in the past, when we try to deploy the visual motor learning, it's too difficult for us to learn something. So instead we try to use the most simple form like the delta action. I think in the future, I think we will need to try the continuous action, and I think it will be extend easily.
You said it was like really difficult.
To learn
Was
something.
that at the beginning? Is it still very difficult? Like, is there a reason now you think any reason why you would want to stick with discrete action versus moving to a continuous action at this point in time?
I think I have tried the continuous action and the result always been worse than the delta action in the real robot. I have no idea why I have some intuition. I would guess that there is a significant discrepancy between for the sim to real, and I think it will have more overfitting using the continuous action. But we also
Can you explain that sim to real part? Because I feel like
Mhm.
the sim to real discrepancy would be the
Below.
same whether you were doing discrete or continuous.
Yeah. Let me try to explain the sim to real part. So I think there's a lot of the sim to real problem there.
But I guess at the highest level, I was thinking the discretization would
Yes. I
equally
think
suffer either way from sim to real. You think it would be better or worse with it?
currently
One way or
I've
the other.
tried it and
Okay.
it worse. I think I need to find some way to fix it. Uh, I think not. I just guessing. I just random guessing. It is just because the sim to real problem.
Okay.
If in the training, sometimes it will have some overfitting problem. So when you have a discrepancy, it will be overfitting to the training scenario. So evaluation is when the evaluation distribution is not the same as the training scenario, it will have a worse performance. So I guess we have a lot of the domain randomization to avoid some discrepancy because we are using the depth estimation, right? And the segmentation method. And this method will have errors in this kind of the method. When we try to deploy it to the real scenario, there will be a gap for our components. I think that will be a main bottleneck.
Okay.
Yeah.
So I was just looking at some of the success rates that you were showing. I think especially on the ones that require precision, like needle grasping, you're looking at 70% success rate. Is that about right?
Yeah, let
And
me switch to that slide.
okay.
So I have
Is it just in
question.
general?
Yeah.
Oh yeah, go ahead, Sam.
I have one question for expert like you and Daoqi. When we call successful way, is it just based on he can successfully grasp it, or do we have other like quantitative measurement how good they are grasping? Because in control well, we have a lot of kind of quantitative measure like the acceleration speed or
Yeah,
overshoot. But in AI world, looks like people are more like a binary result, either grasp or not grasping. Is it something you guys can add some more color here to improve the quality of grasping? Or that's something I want to ask because a lot of time when I look at the paper, I don't know whether this is a trend or not.
Yeah,
Yeah,
I mean, I would say that's all
yeah,
binary.
can I answer that question?
Okay.
Oh yeah, go
I
ahead.
don't know what if you know how to answer, because that is something I have something in my mind for all time. I don't want to ask you because these two experts should be able to answer that question.
Since I only showcase some results, and there's another matrix for me. We call it the grasping score, which
Okay.
has consider the like the time computation
Okay.
computation time
At least you
in
have
that.
computation time.
Yeah,
Computation time. Okay.
in our paper, we showcase that method, and we show that this is the success rate, and the computation time is something in the positive correlation. And if the success rate is high and the grasping score is also high,
Okay.
and it's
But
also
you only have
fast.
just two dimensions, either success and then with time. Do you have other variable you can use to quantify the performance?
I think that, let's say, the safety concern will be our
The
next.
safety concern is really qualitative. There are so many things in the safety concern.
Yeah.
Anyway, those are
Okay.
open-end questions.
I think, one thing that I would say would be very useful, Sam and Hongbin, is object reorientation for grasping, like especially for the needle. I'm sure you've done it so many times. You pick it
I read
up
that
and then
word.
the object, the needle flips on you, right?
Yeah.
Like that's not, I wouldn't consider that really like a successful grasp because you didn't for that to happen.
Okay.
But it's in your hand, and so yeah, I think there's things like that that could be very useful too.
Yeah, sometimes the
Okay.
object is flipped, and we also count it as a success.
Yeah, just
So yeah, go ahead.
just to add a little bit the economy of trajectory. So the length of the path is sometimes also being measured.
So the length
Yes.
of the path is just based on the like a shortest distance or some sort of efficiency. It's more like
Based on the distance, based on the kinematics, the recorded
Okay.
distance.
Okay, good. Because I have a lot of kind of question about this area because I'm not good at. I don't want to change your benchmark style, so I want to keep using the standard AI guy's style for him. Otherwise, I will make him to graduate in another 2 years. So he stay with your field, and then as long as you guys are happy, I'm happy.
If you don't mind, I have two other questions. I'll let the others.
Yeah, definitely.
So this for one question is, with a success rate like you're showing, I think one question I would have is, have you tried the fully model-based approach? Like just model everything, do model-based control, throw in some adaptive control if you want to, but something that's like, all modeled. How have you thought about that, or how well do you think it would do?
Yeah, currently we don't compare with the model based. What you say is the model the environment, and then try to like the grasping something. And I think in a general perspective, there will be some limitation in the modeling approach, like the limited generality and limited robustness. You need to try to model something, and then you need to like have a assumption or something in terms of the object. So our method do not need to assume something. We can grasp anything without changing the algorithm or without retraining. Yeah.
So let me just like push you on that a little bit, right? Which is that I think it's easy to claim generality, but then you have a problem of overfitting, right? And it's overfitting. Overfitting does exist, of course, right? And out of distributions definitely exist as well. But in this case, they're not explicit, right? So you don't know, you don't really know what defines out of distribution. You don't really know where overfitting is. And so in the model-based approach, even if you have like a few parameters that you are adapting, they're known parameters, right? And they're explainable. And so I agree that it may not be as generalizable, but it's something that you can build up. Like you can keep engineering, right?
Yes.
You can keep
Yeah,
pushing
yeah.
engineering and getting it to expand. Whereas the other side, you have these things that are, you can't really pinpoint them down, right? So given that you've done this for your, PhD, like how do you see the two sides of the coin? Like, how do you see both of the sides? Like, do you feel like this would have been easy? You could do this with model-based approach. Do you think that the future is model-free? Learning. What's your viewpoint?
Yeah, let me try to express my thinking. Two sides of the approach is promising. From my perspective, I think if you want to choose the best performance, you would choose the model-based. If you want a high generality or robustness, for me, I will choose the model-free approach. And I think it will have a more robust and generality performance as your data, your training data has been more diverse and more the amount the quantity increase, the performance will be much better. So I think both methods will be promising, but depends on your application. I think when you talk about the model-based approach, we will mention about a umbrella of some manipulation objects, right? And I think you need to choose carefully how large the umbrella is and what type of the method object you want to manipulate. So if you don't have an idea, you just choosing the model frame approach. So there is a lot of the engineering domain specific knowledge in the model-based approach. But for those without the engineering background and they want to try the brute force method, I think they will try the model-free approach. Actually, I've done something that like the model-based approach for the quadratic compensation, and I know the difference between the model-based and model-free. And for the performance, I would definitely choose the model-based. To be honest.
Okay.
Yeah.
And so, like, if I was going to ask you, 20 years from now, the surgical robot is autonomous. Would you want it to, given what you are doing now, where you think the trajectory of things are going, would you want it to be a model-based method or a model-free method? Or you feel like they must have figured out some hybrid of both?
Yeah. I would say currently I will choose.
You're under the table, okay? You're the one that's having surgery on, okay? So
yeah,
which one would you want?
Yeah, I would say if I start a company, I would choose the model based. But I would say the future will be the model free. After a few years or tens of few years.
Yeah.
So
All right,
we have
thanks.
two students, Michael. Hongbin is purely like an AI-based approach without any model. But the other student also working on AI with deformable object manipulation. He creates some sort of hybrid approach. So
Nice.
part of model-based, part of AI, and depending on the structure, you combine them together. Yeah, I don't know what he picked, but I think if you guys want to put more like a boundary or constraint, at some point it become more like a model based, because how can you add hard constraint in AI approach?
It becomes more like a heuristic, right? The model free it's
Yeah,
all heuristic, but you're bounding all the heuristics with
that's
constraints and
true.
things
Because
like that,
once
right?
you have hard constraint, I think it's not purely an AI approach. It's not the general AI approach. But anyway, you guys have different idea. But from my naive like optimization knowledge, I think it's a little bit more like a hybrid. But anyway,
I think it's great to have both sides, at least. Like it sounds like you guys are working side by side with people that are doing everything.
Yeah,
from
I'm
model
comparing
to model
both
free.
and
So
see
it's
which
good.
one can move forward, because I can pretty much if I use the hybrid approach, I can protect the like overshoot in the uniform. It won't happen. But of course, the successful way will drop down. I believe so. then you need more learning. And then he's sorry about that, Ben. I shouldn't discourage you. Your success rate is so high because you didn't protect the boundary. I believe if you want to protect the boundary, your success rate will drop significantly. Because pretty much you need more data to learn, and all your method may change a little. But anyway, this is open-end question. I cannot prove it at this moment, but I will find another student to figure it out.
But from my perspective, the success rate is really low, and compared to the Johns Hopkins results, they claim 100% success rate for needle picking.
Back one they have very artificial environment, so it's a little bit different. Yeah, I guess so. So you are doing with some more generic environment.
Yeah.
I stop here. Sorry about that. I talked too much. But
Okay.
next question, Michael.
Continue. We have to keep the time. Yeah. So, Michael, more questions?
Oh, I'm done. Yeah, please. No, I'm good. Thank you.
Okay, thank you. Thank you, Ben, for the presentation. I think I'm pretty familiar with your work, and some of your work I'm even co-author of your work.
Thank you too.
So I think for your actual current development, I don't have much question. I'm wondering what is your plan, and especially you mentioned multiple times about your future work. So I want to know more about your design of your study during the PhD period, and also, I mean, afterwards. So I'm wondering, see, all the current work that you are included in the thesis are about needle grasping. So as far as I remember, you already got very good success rate in your RSS paper for the needle grasping. So the method is quite, I mean, robust with different background and environmental, I mean, shaking and smoke, etc. So why didn't you move forward to apply the needle grasping to some downstream tasks, such as bimanual handling of the needle, or the needle repositioning, or the suturing, or even you might compare your autonomous grasping with some human performance to check whether this kind of autonomous function has any benefit compared with human manipulation. But instead, you didn't do these things, but you choose another method, I mean, to further conduct the same technical task of the needle grasping. So what was the difficulty and then time, and have you tried to consider moving forward with your research task for this autonomous grasping?
Thank you for your question. I think there is two questions. One is why I do not like implement the RSS work to the other surgical tasks, and the other is why what is the architecture? And for the second question, I'm still improving the algorithm based on the RSS approach. We don't like abandon our previous design. We just improve upon that. And for the first question, we have a different benchmark for the grasping. So we only allow the gripper close once, and in our RSS paper, we can close multiple times. And in our previous benchmark, it will take longer, but the time will be much longer since we are using the 8 times speed or the 4 times speed. In our latest work, it will be much quicker to achieve the grasping. So here we showcase the comparison of success rate between our current work and with RSS work. So this is RSS work. So in the new benchmark, it didn't improve anymore. It didn't show really good results. It just have a 0 success rate. So when you only allow the gripper close once, and it will have a much harder problem for the grasping. Is that answering the question? And I think, yeah, definitely our work can be extending to the other surgical tasks, since we are using the data-driven framework, and it's easily to directly train to the other tasks and try to see what happens. Yeah.
Yeah. Follow-up question. So let's suppose if you have a perfect grasping model now, that is pretty fast and pretty safe. So how would this benefit surgeons? I mean, have you considered human-robot collaboration? See, if you do the grasping automatically, and then the next step has to be done manually. For example, you insert a needle into the tissue, etc. Then, how would this autonomous function be integrated into the manual manipulation so that it can, I mean, benefit the help the surgeons do things faster or safer rather than interrupt them doing the works again and again?
Yeah, from my perspective, it will be easy. And I think the hardest part is the trying to grasp an object in a random position. And when you finish the grasping, you can switch to a predefined trajectory, and you can use some script policy, like you program some policy and try to hand over to the other arm of the surgeons, right? We can just switch from the RL policy and like the traditional control policy or the script policy.
Okay. Have you discussed with any clinicians about your hypothesis of their use cases in the implementation?
No, but we will try to do it in the future.
Okay. Okay. All right. So I don't have other question. Thank you.
So, yes.
How about you, Professor?
Yeah, I just maybe need be more question about your contribution. You mean this part for the visual several grasping with a word model, right? So
Mhm.
can you explain a little bit more? So what's
Yeah.
exact contribution or your novelty here?
Novelty. Okay. Wait a
Yeah.
minute. I think we will be in our contribution here. The novelty should so for the perception pipeline, we propose
No. I mean the first
yeah.
part for the grasping with a word model here.
Oh, we actually don't really contribute too much on the word model algorithm. We directly use it, but we in terms of the detailed implementation, we prefill it with some demonstration trajectory, and I think in terms of wait a minute, the second work we use a virtual clutch, which is a novel proposed technique to solve the issue of the original word model framework. So it try to solve the inaccurate initial latent space estimation in the robot manipulation.
Your clutch, that means you have a hybrid implementation. It's a two approach. One's PID or another is like
yeah, one RL policy, one
RL.
like the PID, one is the virtual clutch policy. We have a hybrid policy.
So how the any special contribution in the clutch, how to switching between
Oh, yeah,
two approach.
Yeah, that's a good question, and I think we just have a naive approach to switch. We just switch depend on the time. We based on the time. Wait a minute.
Okay. Based on time, based on phase. Yeah, phase.
Yeah,
You have say phase 1,
phase.
2, or whatever, right?
Yeah. So let's say the time is less than some predefined threshold, and we define as the virtual clutch policy. I think there are a lot of room for improvement. We just think it naively.
Okay.
Yeah.
Okay.
Yeah, and this is
Okay, I understand. Just a minor suggestion for the hybrid control. In the robot control, the unit means position and force control. If you want the terminology wise.
force control.
Yeah, the usually mean position and force control, the hybrid control. If you use a terminology for robot control. Yeah.
Okay, you mean the
Knowledge wise,
knowledge wise, we do not really.
Yeah, hybrid control in robot control in robotics using position and force control.
Oh, okay.
Yeah, it's a very famous paper. Yeah.
Sorry, I don't have too much background on the control theory.
In robot you work on robot control.
Robotic control. Okay.
Yeah, I suggest you do not use this hybrid control. hypercontrol usually means position and force control. Okay.
Okay. Yeah, thank you for the suggestion.
Yeah, I'm done. So, Sam,
Yeah. Just very simple question. Because I know exactly what you are doing. And then my main question for you is I saw one of the things you are talking about grasping. When you grasp different object, I saw you intentionally put some soft object there.
Yes.
So if you put some hard object, do you think your approach will work? Because it looks like your learning approach can only learn how to grasp some small hard object. So when you put a big object, if they are not soft, you may break something while doing the grasping. Because at the end, you put some sort of tissue or some sort of spongy stuff at the end. It's not just needle.
Yes, I know your concern. Right now,
Or
the rigid object is only the needle, and it
the
will.
rest of the object, although they are different object, but you intentionally pick some soft object.
yeah,
So
actually, I asked this question before. He answered.
Sorry.
he did not answer that question.
Yeah. That's a good question. I think if you put the hard rigid object on a rigid platform,
It's
you
very
need
hard.
you need a really high accuracy
No,
control.
I only talk about the soft object. So first, the object so you have object and the platform. So assuming
Yes.
the platform is soft, well,
Yes.
now you have a needle and you have a different size of spongy object, am I right?
Yeah.
Those are bigger than the needle. So
Yeah.
I assume your model they learn can only grasp a small needle. So that's why when you grasp a big object, they will keep squeezing up to a point they are getting very close to the needle size, they will stop there. So that means that if you put a object as big as the spongy, I don't know, spongy object you pick, but they are rigid. Do you think your approach will still work, or you will break the instrument right away?
I think as long as the platform is deformable, so the ground, and when the object is placed on the tissue or something soft, it will when you push it, the platform will also move along with it, but it will create some tension.
Are you talking about object is deformable or
the object is rigid? The object is rigid.
Object is rigid, but
the platform is
can be
deformable.
soft. Okay.
So when you squeeze it, the platform will be moved along with the movement. But yeah, that will be a little bit harder. But I just showcased the needle picking, like the rigid small needle placing on the deformable objects platform. I think it's slightly harder, but not too hard to apply our method to picking a rigid large object on the platform, or a deformable object.
So I assume you need to relearn all the things.
Relearn all the
Right?
things. Yeah, because a large object, I think. No, I don't think so. I don't think so.
You don't think so? Okay, we can. You can do some experiments, see if it works. The same size as yours.
Sorry, just to clarify, your action space is not torques, right?
Yeah.
It's position, right? And so, okay. Anyway,
I don't think you need to relearn.
Yeah, but I think it's much better to have some object that you have seen in the simulation. The target object, you can put some random shapes, which you can put some large shape of the target object and the small shape. Right now we only put some like the needle model and some
No problem.
cuboids
I
and
got it. Yeah. So you just want to put different variety of object and learn about it. And the last question is about, well, now you only learn about the position. Assume if we can give you the force data, do you think the same approach will be scalable to incorporate force inside? Will it make it will it help to converge, or it will actually make it worse because your motions, your overall dimensions are far higher than before? I don't know. That is something I have been thinking about. So
Yeah.
how do you think about if you add additional force sensing data into your training process? How are you going to incorporate them into your structure?
Yeah, that's a good question. If you try to incorporate the force sensor and you have force signal, for our approach, we can just use the force sensor. The force signal is only a low dimensional signal input, so it can try to use it as the low dimensional signal and broadcast into a high dimensional image plane, and it will be portable for our method. And I think if the force sensor helps our method, it depends. If the force sensor signal is very noisy, you need to find a way to try to like reduce the noise.
No.
Yeah.
I
We
don't know
try,
when you think
there is a
noise is based on the actual noise or the noise that relevant to your objective.
yeah, when the signal to noise ratio is too low, you need to find a way to fix it. And I think there will be a good way to quantize, like discretize some level of the states. Like if you're touching something, it will give a binary of 1, and if you do not touch something, it will give a binary of give a 0. So you will have a binary input, and I think that might help the noisy false input.
Okay, no problem. I
Okay.
think that's it for my question.
Okay, thank you. So we are done, right? So, Mr. Lin, would you please excuse us?
Yes.
Can you transfer your host to Sam or me so that
yeah, I'll try to assign the host to you. Let me check. Make host. Change host. Do you receive the host?
Yes, okay.
Okay, thank you
So
for
please
all.
leave. We'll call you in again later on.
Yes, thank you.
Okay, please leave. Please
thank you.
leave.